All right, so the technique I'm trying to get through to you guys today that we're going to continue to practice, basically in this first calculus course, we're going to go backwards on the chain rule. And I know most of you would be like, that's the worst one. But when you do integration, it's actually the easiest one. So you'll see the other techniques, like if you're wondering, well, how do you go backwards on the product rule or quotient rule or other things that we've done? That's the next calculus course, so you would see that later. They are significantly harder to do than the one we're going to practice. So basically what we're trying to do is we're trying to match up a pair. And the pair that we're looking for is a function and a derivative. So let me highlight to you where that is in this. There's a, oops. Sorry, let me just, don't want that one. There's a function g and a derivative g prime. So basically that's what we're trying to find here in this pattern. If you look at an integral and you go, oh hey, I can see the function and its derivative, then we've got a chain rule hidden in there. So let's see if we can do that on this first example. Oops. Okay, so what do you think? Which one, left or right? Which one's a function? Which one's a derivative? The right side is? Okay, so there's my function, and there's my derivative. Okay, so if we can recognize that product, then we can use the chain rule backwards. Okay, so what that means then is if I'm taking my integral, here's the substitution I'm going to make, and that's where the name that's where the technique gets its name of substitution. So what I'm going to do is I'm going to take out the function here. So I'm going to say let u equal e to the x plus x. So we don't normally write this, but because we're just learning this technique, it's the function that I'm trying to take out. And what I'm going to do here is du dx is e to the x plus 1. So I know then that du is going to be e to the x plus 1 times dx. And look at what's already in the derivative here, or sorry, the antiderivative. It's that piece and a dx. So now I can make the two switches that I need to. The first switch would look like this. Got to change my pen here. It would be the integral of e to the x plus 1, and we'll put this substitution in here of u dx. And this is weird because there's two variables in this, and we're doing it with respect to x. So what I want to do is change this integral to be in terms of u. And here's how you get there. Du is equal to e to the x plus 1 dx. So these two pieces here, I can plunk that in, and I'll get the integral of u du. They're equivalent. So now if you look at where we started life and where we've ended it, this is like, yuck. It looks really bad. Maybe you'd like expand it or do something else, but look where we are now. We just have this integral here. And that's just power rule. So let's go backwards then. It'd be u squared over 2 plus a constant. And what is u squared? That's e to the x plus x over 2 and a constant. So it's quite difficult to see that when you're just getting started, but the technique here is going to help us find out, where to make the substitution. So I'll keep doing these ones with you for get us worked up on this, but let's just review here. Who are we making a substitution for? We've got a function and a derivative. Which one are we going to try and take out of it? The function. Okay, so which ones do we have here? Left side and right side. Which one's a function? Which one's a derivative? Yeah, so it's turning out that way, but it doesn't always, right? But okay, we recognize which ones are paired up. So who's going to be, what's the substitution going to be? U equals, what am I going to put in here? Tan x plus 3, good. And remember, if I was to just jump right into that, here's what it would look like. You don't have to write out this step when you're doing it, I'm just doing it to show you why the next part is necessary. This is an integral with two variables now, a u and an x, and it's in terms of dx. So we can't work with this. It all has to be in terms of the same thing. So that's why I have to pull out this piece here, this x and this dx. And yes, in your world, it'll always happen nicely because they're made to work out that way. So what we'll do here is du dx, oops, sorry about that, du dx is secant squared x. Now, the thing that I showed you last time, I will do it again because I've had practice at this and it's easy for me to see where they get switched. So for example, if I go du equals secant squared x times dx, then I can see the pattern just right there and I'll swap them out. But the other thing you could do is, as I said earlier, we're trying to get this in terms of u. This is really what I want to work on, is how do I get that from respect to x into with respect to u. So the other thing you can do, and some people like this when they're getting started, is if I solve this for dx, maybe I'll go like this, du over secant squared x is equal to dx, then that tells me what I'm putting in here, right? Make the switch for dx, so I'll get secant squared x times u times du over secant squared. So those are gone, and I end up with u du, which again is just back to power rule. So I can use power rule on this. It'll be u squared over 2 plus a constant, and we said earlier that u is the tangent of x plus 3. Oops, not tax. It is almost tax season, but tangent of x plus 3 squared over 2 and a constant. So whichever way you prefer, the one we did here on the left side or substituting for dx on the right side, either way is going to get you the correct answer. It's up to you on personal preference, okay? So in the next couple examples, we're working with some polynomials. Maybe the last one here we'll do together, but I think if you're getting the hang of it and I give you enough time, hopefully you can figure out the pattern here in this one. So look for a function and look for its derivative. See if you can make the substitution on them. Okay, so it looks like a lot of people are having that sort of aha moment where they've realized you can't just jump right into autopilot. A lot of people saw this and they said, oh, I recognize this derivative is part of this function. And then as I went around, I saw most of you were pulling this whole function out. So the problem with pulling that whole thing out, if this is the pattern you're using, x squared plus 1 to the 4, then its derivative is going to be 4x squared plus 1 cubed times 2x. And that is not what you found. That's how you know that you didn't find the right set of partners. It's not to say you weren't initially correct. It's just that you took too much away from it. The one that you're looking for to get the derivative that's there is just this. If all I did was take x squared plus 1 out, then its derivative is 2x. Those match up to the parts in my problem. So that's what I'm going to use for my partners. A function of x squared plus 1 and a derivative of 2x. Okay? So I'll make my substitution here. Whoops. Let u equal x squared plus 1. Du dx is 2x. So how many people like doing it dx equals? How many people like doing du equals? Okay. So du is 2x dx. That means I can see the pieces here that'll get me a du. So I'll have u to the 4 du after I make my substitution. This piece that I have for u, that's why I'm raising it to the exponent 4, is that's how it would go in the original antiderivative here. And again, that's not so scary. All that is power rule now. So that's a lot easier than where we started with this mess right here. So now I'm going to have u to the 5 over 5 plus a constant. and u is equal to x squared plus 1. So x squared plus 1 to the 5 over 5 plus a constant is the antiderivative. Question? Okay, let me clear some of the mess here. U is this, correct? So that highlight right there is u. Okay, so when I make my substitution, u has been raised to the power 4. Basically, I was saying you can't take this whole thing out, because if you do, it doesn't have the derivative you're looking for. You haven't matched a function to its derivative. So I can only take this much of it out, the highlighted part. And then that means if I only took that out, I would have u to the 4 when I rewrite it. So, you know, that's one thing for you to think about. Don't get scared off by the exponents, because it's easy to do power rule, right? Power rule is probably the simplest of all our rules and techniques that we use. So that's not a scary thing if you're left with an exponent. Okay, the next one again, very similar to what we've already been working on. See if you can find who the partners are and make the substitution through this. It looks scarier, but it's the same technique. Where's the function? Where's its derivative? So just show of hands, how many people think they've matched the pair okay? Maybe you're not all the way there, but you think you found the right pair. Good, so that's where you should be at right now. Hopefully you can see the pairs, and then we'll work this one through. So what pair did you have between these? Okay, 1 minus 2x squared. Yeah, that looks like a good pair to me. So let u equal 1 minus 2x squared. So du is negative 4x dx, and that's this piece right here. So I can rewrite this as the integral for du over u squared, which means I've got the integral of u to the negative 2 du. So using power rule, I go up 1 and divide by that. So here u is equal to 1 minus 2x squared to the negative 1. And maybe I'll just tidy that up. That's negative 1 over 1 minus 2x squared and a constant. How many people got all the way through that one? Good, genius, okay, great. That one's a little tougher. Hopefully, again, with a bit more practice, that's something that we're all doing, but this is the technique. We're trying to match partners. So if you're as long as you're finding the partners right now, we'll get there. Uh-oh, trigonometry. Don't give up. You can do it. I believe in you. See if you can handle sine, cosine, and maybe you can even handle e to the 5x times 5. Okay, so it looks like we got some good progress here. One thing that's helpful for those of you who have a hard time seeing it, especially with trig, you know, it's not a bad idea to remind yourself what you're looking at, right? Even though it's in the middle, this is what you're talking about, the cosine squared. So if I want to pair some stuff up, and people are like, oh, well, which pair do I pick? Some are sine, some are cosine. Then the one that you want to pick here is the cosine, because it's inside that power there. Otherwise, if you went the other way, this would be the function you're choosing. You'd be left with the cosine squared, right? They don't match up that way. So here's my function, and the sine is going to be my derivative. So I'm going to say let u equal cosine of x. Okay, so if that's the one that I choose, then what we're going to have here is du dx is negative sine x dx. Okay. Oops, sorry, I went too far. Just negative sine x. So du is negative sine x dx. I will work it through the other way if you pick the other pairs to see what it is that you have, but let's talk this one through first. So this is really close to what I want. It's not quite what I want. So how do you think we could fix this? Well, there's a sneaky little technique, and this is as far as we're going to go today with, you know, how else we could substitute. We're going to sneak a constant in because a constant won't change it. But I can't just throw a negative sign in here because it's convenient. I also have to do the same thing to balance it out. So a negative and a negative would cancel each other out, right? So that way, I got the piece I'm looking for. This is going to be the integral of u squared du, but I've got to have that negative out front. Okay. So again, if you're wondering how far are we going with this today, that's it. We're just going to worry about balancing it out when we almost have a pair. We just have a difference by a constant. So this will be negative u cubed over 3 plus a constant, which is going to give me negative cos x cubed over 3 plus a constant. Okay? And again, if you're ever not sure, you can always take the derivative to make sure you did, you know, do this correctly. If you take the derivative, you should end up back where you started. So let's pretend for a second now that you didn't pick the right pair. Does anybody, I did say so, but how did I know which one? You know how I knew that I was picking cosine as my function and sine is? Yeah, cosine squared. If you did it the other way, and you don't need to, you know, keep this in your notes, but I'll just show you what would have happened. If that's my function, then I'd be saying that my derivative needs to be cosine squared x in order to partner up, right? And I don't have that. That's not the, it's not going to pair up like you expect. So at this point, hopefully you'd say, okay, yeah, I picked the wrong pair. They don't match because I'm only going to have a cosine. So I know that it's not what I want, because otherwise what I'm going to be left with is a cosine. There's going to be a cos x. Well, there'd be a cos x squared u dx, and then cos x. Only one of them is going to get pulled out here, so I'm going to have cosine x u du, and I still have this problem of two variables. So at some point you get stuck, and hopefully you just recognize that you picked the wrong pair. So in our world, as I said, the questions are going to be such that you don't, you know, they will pair up nicely. You'll see a derivative in a function. Okay, so for the second one, yeah. Well, another way you can do this as well, like this is kind of the hotshot way of doing an integral. You know, it's most of you are going to gravitate this way, but if you're not sure, the way to check it is you can go with dx as well. So let me show you what it would have been. If I would have done this, I get dx, I'll write it this way so you can see it, du over negative sine x is equal to dx. Let me write this in purple, and I'll rework it in purple for you. So then my integral that I started with would become u squared sine x dx, and I'm going to make that other substitution here, which is to take dx out. So I'll have sine x du over negative sine x. And the signs would be gone. And what I'm left with is that negative like we had. So that'll be negative u squared du. So when I do it that way, I don't have to think about balancing it out. But anyway, either way is going to work. But like from my experience, students tend to start doing the du, this one here, once they've practiced. Well, I have to balance it out. I've got like derivative of cosine is negative sine, right? I don't have a negative sign anywhere in this problem. So I can't make that switch. They're not equal unless I bring a negative into the problem. So what I did was I said, let's add a negative sign, because that's what I want. But I can't just magically throw a negative in without changing things. So to balance it out, I'm going to multiply here Negative times a negative gets me back to where I started. So it's kind of like when you add 1 to the left side of an equation, you have to add 1 to the right side so things balance out. Whatever you did on the inside, you have to balance on the outside. Okay, so in this next example here, what substitution would you make? Good. 5x, because the only other function here is a 5. So that's the pair, is 5x. Du dx is 5, so du is 5 dx. And again, there it is. So I'm going to have the integral for e to the u du. And this one, what's the antiderivative going to be? E to the u. It's your favorite. The derivative is the same as the function. The antiderivative is the same as the function. So this is just going to be e to the u plus a constant. And for us, that's e to the 5x plus a constant. Okay, so let's practice this idea of changing things by a constant. So if this is the values that I'm starting with, I'm going to try the first one with you, and then I'm going to let you go to it on some of these for practice. But basically, as I said, our difference is going to be we need to balance things out. Okay, so let's start here. Do you see a kind of pair? I mean, yeah, they can only differ by a constant now. That's the only difference, is we multiply by a constant. So can anyone see a function and a kind of derivative?
X squared plus 1x.
Okay, so if I look at this as my function, this is on the right track. I'm going to walk you through what happens. What I'd like is du dx is 2x. I don't have a 2 though. So here's what I could do. Du is 2x dx. So I need to get a 2 into my problem. So here we go. Ta-da! That's magic though, right? Can't just do that. Okay, what do I have to do to fix this? A half outside will balance it out, right? So if I put a half here, there's no change now in the antiderivative. Okay, so now I can see how I'm going to make my substitution. I'll have 1/2 the integral of u squared du, because 2x dx is going to allow me to switch that to a du. I have all the pieces there. Now I can make the full switch. So again, for those of you who kind of are mystified by what happened, if you're mystified, then you need to go this route. There's no shame in it, okay? It's just a different way to solve the same problem. That's to consider this as du divided by 2x is dx, and then swap it out. So in black, I would have the integral of x squared plus 1 dx, and I'll make my substitutions this time. That'll be the integral of x and u squared. And dx is equal to du over 2x. So those are gone. And what I'm left with is this half on the bottom. So it's going to be 1/2 the integral u squared du, which is exactly the same as what we had in the other way, right? Pick a way that you think makes the most sense to you. If you like balancing it out, then that means you do this technique. You find du, you balance the integral, and you substitute. If you don't, if balancing it out is confusing, then substitute it directly like this. Okay? All right, so these next examples here, as ugly as they might look, they all follow the same pattern. Find a function and its kind of derivative. The only difference is you have to figure out how to balance it out, whatever constant is missing. Oh, sorry, I guess I should actually finish this question then, hey? So that'll be 1/2 u cubed over 3 plus some constant, which is u cubed over 6 plus a constant. What about this? Should I have done that?
No.
How come?
Because
It'd still be a constant. Yeah, so math with constant there is kind of fun because dividing by 2, it's still a constant. Adding 1, it's still a constant. If it's still a constant, we don't need to do that. So basically, that's why I didn't write it in my final answer. It's going to be some number. That doesn't change it. I'm going to try and catch up to you, so if you want to just double check over, it looks like it's going fairly smoothly.
Yes. I know. That's what I asked you. And I saw that before.
Okay, so in this one, I have 4x cubed as the derivative, but what I've got to work with is 2x cubed. So the balance is to multiply by 2 on the inside, so divide by 2 on the outside. Now everybody's balanced, and I can make the switch. These two pieces will turn into du, and now I can find a much easier antiderivative using power rule. And since u is equal to x to the 4 plus 1, this is my final antiderivative from where I started. Now, this one's a little trickier, so let's talk about it. We're working through this, and the first thing we try to do is match up a function and its derivative. So what function do you think I'm going to work on here? 4x cubed plus 1, yeah, that's a good start. So let u equal 4x cubed plus 1. Then that means the derivative I'm going to get is 12x squared. And it's only 9:30 in the morning, and your teenage brains are still sleeping. So if you have trouble balancing this, then don't go and use the du version. Try it like this. dx is going to be du over 12x squared. And then when I make my substitutions, oops. Now the x squareds are out. I don't have to think about balancing it. It is equal. But all I got to do is, I suppose if worst came to worst, you could write it like this. But hopefully, even at this early stage in the morning, you can tell me how that reduces. 3 over 2, that's right. So we're dealing with 3 over 2. And it's easier if I think about this as 1/2. So that means I know the next exponent is going to be up 1. So that'll be u to the 3/2 over 3/2 times 3/2. So I'm just going to end up with u to the 3/2 plus a constant. And here was what my original switch was for. It was 4x cubed plus 1. This is all to the 3/2 plus a constant. Okay, so the key is that you're able to balance. Whichever road you take, as long as it's balanced, you'll be able to make your substitution. Has anyone had a chance to try the last trig one here? Okay, maybe I'll give you another minute to work on your own here. All right, so in this instance, if I'm thinking about which one is a function and which one's a derivative, this is the one I'd like to use for my function, because when I take the derivative, that plus 7 will disappear, and I know I'm going to be able to line up to this. it won't work the other way around because plus 7 doesn't magically appear when you take the derivative of cosine 1/3 x. So the pairs let u equal sine of 1/3 x plus 7. Du dx is going to be 1/3 cos x, 1/3 x. So for what I have, right now I have a cosine 1/3 and a dx, but I need to have a 1/3 in front. So if I put this 1/3 in, I'd have to multiply by 3 in order to balance. So that means I'll have 3 and the integral of u du. So 3u squared over 2. And for us, that means 3 sine of 1/3 x plus 7 divided by 2 and a constant. Oh, thank you, yeah. Squared. Okay, so hopefully you're at the point where this isn't going to scare you off. It's still chain rule. All again you're looking for is the function and its partner. So this is where we'll leave off today is can you attack and conquer these last two antiderivatives? Okay, so the first one I've got for you here, it's harder to see, but x squared plus 2x and x plus 1, those can partner up. Here's how it's hidden. It's 2 times that. Generally, if you're trying to think about why are you substituting, you're trying to take the worst part of it and make it disappear. We're trying to take something that's very complicated and try and find a simpler version of it. So if you're not really sure where to start, generally you're looking to substitute for the worst thing there, right? Make the worst thing go away so it's simpler. So hopefully working it through, you end up with 1/2 e to the x squared plus 2x. Again, you can always double check by taking the derivative to see if you've got it correct. And in the last instance here, the worst thing that I've got, I have a bunch of pieces I could try for, but this x squared and that x is what I'm going to shoot for. If I was to bite off the whole thing, if I was to try and do all of that, I won't get the right derivative. There's too many pieces to it. So du dx is 2x, so du is 2x dx. So that's what I'm missing in here is a 2. So that'll be a 2, which means a 1/2 will be outside. So 1/2 the integral of, let's see, I'll just make the substitution. Sine u du. So what'll have an antiderivative, sorry, what function has a derivative of for sine? Good, it's negative cos. And for us, that's negative 1/2 the cosine x squared plus a constant. All right. So, how's it going? You still with me? Okay, that's where we're ending today, so good on you for hanging in there.